I want to welcome Beverley Wemple. Thank you for coming back after we rescheduled you 5 times. No, this is the 5th. This is the 5th time.
Is it?
I know, because I found out all those meetings. You probably were a little bit tired of getting those from me. So, Beverley knows only a few people here, and I thought it might be helpful if we quickly go around the room so she can place faces with you.
I know.
Yeah, it'll be
Steve Fisk, work for the biomonitoring aquatic study section. Rick Hopkins, our ecosystem restoration program. David Pasco, ERP as well.
Ryan Fitzgerald, and I used to work here.
Are you? I thought Jeff on you.
Mike. Jim Deschler, with the biomonitoring guys.
Morgan Bell, Rivers.
Jim Ryan, watershed coordinator.
Like Rivers. Helen Carr, stormwater program. Jenna Calvi, stormwater program. Angela Wakeman, Danielle Garcia, wetlands. Sasha Peeler, Rivers program. Section Alexandria, Rivers.
Phil Nipper, stormwater. Eric Davis, Rivers. Better book.
Emily Shelley, stormwater.
Ethan Swift, and one of the watershed coordinators.
Christy Witter, stormwater.
Frank Gianrigo, trans operations.
Gary Sabrum, forest parks and recreation.
John Armstrong, Beach.
And Swampert, Rivers. Ben Coban, watershed coordinator.
Carrie Dillon, ERP.
Justin Kenny, IT/ecosystem operator.
Stacey Pomeroy, Rivers. And Michael Stickney, ERP. And it's a real testament to the interest in your work, all the disciplines that are represented in the room here. I want to give a special thanks to Justin for helping to set this session up. And we get to use the newly installed smart board installed less than 24 hours ago. So we'll give this a test run and see how it goes. And this session will be recorded and available on YouTube on future timing, because there are many people who are not available right now who are very interested also.
So I can send it to my mother.
You can. You can. If you want to be seen, we'll take the cap off that little microphone there and take a picture of you. So thank you. And I asked Beverly if she would actually mention a little bit about her background before she came east, working with groundwater with the Forest Service.
Well, I think I know at least half of the people in the room and a bunch of people who are on the webinar. Hi to people who are coming in remotely. So that's probably as much a testament to how long I've been around here as it is to interest in this. So it's nice to see familiar faces, and to put some faces with names that I've corresponded with by email. So when Michaela asked me if I would come and do a seminar here, she asked if I would just come and do a seminar on my road work, and I interpreted that pretty broadly. The ERP program has been supporting the latest project that we've been doing, but I thought I would go back and sort of start with this Lake Champlain Basin program project that we started back in 2010. And I got into that because I had done my graduate work in Oregon working on hydrologic effects of forest roads. And when I left there, said I'd never work on roads again. And then when those RFPs started coming out from the Basin program, I thought I better try this. And so I got back into it at that point. And in some ways, it felt like comfortable ground again.
Hit them, try hitting higher up.
Slide. Okay. So this sort of a theme will look familiar to all of you all. I just put it in here to set the context that this work that we've been doing, and I say we, I'm going to say we throughout this because I want to make sure I acknowledge my collaborators, Donna Rizzo, Lesley, Morrissey, and Don Ross, who've been very involved in each of these projects I'll talk about today. Can you guys hear me?
Yeah, can you hit that pause button that you hit by accident?
Oh, did I hit the pause?
Oh, we fixed it.
Okay. Can you guys on the phone here, or they wouldn't be able to say?
No,
okay.
We'll get them.
If you think about the water quality problems in Lake Champlain, and I'll just sort of posit that up until fairly recently, our prevailing thinking has been that the water quality problem is really a lowland problem with agricultural inputs from the lowlands and increasing recognition of what's going on in unstable rivers, thanks to the work that Mike and his group have done and contributing to water quality degradation. But I would argue that if we think about the landscape as a whole and we look up into the uplands, our thinking has been, well, they're really not a problem from a water quality standpoint. And I remember one of my first years here at UVM when I was sort of scratching around for how to develop a research program, and my specialty was in forest hydrology. Mary Watson said, well, we're not really concerned about the forest and hydrologic and water quality problems there. But if you go up into the upland setting and look around a bit, there might be some reason to think that there are some water quality issues that we might need to address in the upland setting. And they're primarily around this fairly extensive network of gravel roads that we have in this landscape. And so that's really the motivation for the work that we took on for the basin program and have continued to work on through a number of other opportunities. So today in the seminar, I'm going to really try to stick to an hour. So if you feel like I'm talking quickly, it's partly because no one wants to sit through more than an hour long lunchtime. I'm kind of impressed that people come out of retirement. But I'm going to try and work through these three studies, distinct studies that we've been working on since 2010. This first one was the study that we did for the Lake Champlain Basin program, and that report has been up on their website for almost a year now. So I'll move through that kind of quickly because if you're interested in more details, you can look at the report that's on the Basin Program website. The second study is one that we launched sort of in part in collaboration with Mike and his group. It was funded by the Northern States Research Consortium to look at whether we could detect any effects of roads on channel morphology in our rivers in the state. And then the third project that I'll describe today is the one that the ERP program has been co-funding. As I work through the presentation today and describe these three studies, I just want to anchor an image in here that we're going to be moving across scales a bit. The first piece of work that I'll talk about involves doing some fairly intensive measurements in the Mad River Valley, but also more comprehensive survey across the Winooski River Basin, and then this study that we did looking at whether we could detect any impacts of roads on streams was conducted using the RGA database that covers the state. And then the BMP study, we come back to the Mad River again. So we're going to sort of move this way and scale and then come back. So this is just an image to sort of block your minds onto the fact that we're moving scales a bit as we go through this. So I'll start with this first of the three studies that I want to describe today. And the goal here was to try and get a handle on how important gravel roads or back roads are for pollutant production in our landscape. If any of you have seen the Basin Program report that we produced from this, you'll know that we had two different approaches in this study. The first approach involved doing a survey of erosional features on the road network, and we did this within the Winooski River watershed, which you're seeing down here in this little bottom left of the map. Each of those points there are road segments that we surveyed. And what we did for this study was to take roughly 1 mile length, or a little over, sorry, not me, or, thanks. Roughly 1 mile segments of road and walked them with the GPS unit and basically mapped any sort of erosional feature that we could identify, rills, gullies, plugged culverts, those kinds of things. And except for plugged culverts, as we were mapping and identifying erosional features, we measured their dimensions, width, depth, and length, so that we could come up with a volume estimate. We also took some bulk density measurements from the road into the ditch so that we could convert those volume estimates into a mass, and then analyze the samples that we took for bulk density for phosphorus concentration so that we could convert that mass of sediment into some measure of phosphorus eroded from roads. These figures that you're looking at on the right side are a summary of about 100 miles, I think, of 100 kilometers of roads that we surveyed, where I'm just summarizing what the frequency per unit length and volume per unit length were that we mapped. So on average, we tended to have somewhere around 10 or 12 features per kilometer of road that we identified. But they were, for the most part, relatively small. So many of them were only about, or on average, they were about 7 cubic meters per kilometer. You know, small features that added up to about 7 cubic meters per kilometer.
Bev, were those kilometer each the same type of setting or different settings that you?
All different, let me go back, all different sorts of settings. So we did the surveys, was that Stacy? We did the, is that me or you?
That's you.
So I just need to touch later or what? I'm not used to this.
Yeah, or not touch it off.
Or no, don't touch it off.
You can.
We did?
No, that's so you can write over it and save it.
Okay.
You got it.
This is study. By survey and survey, we basically came up with a stratification scheme so that we could try and sample the road network proportional to where it was located in the landscape, like slope position, and also road grades. We did this GIS analysis to look at what the distribution of unpaved roads were by road grade, slope position, not so much geology, and then basically randomly selected road segments from that. So we think the segments that we surveyed are representative of the road network as a whole. Go ahead.
You're only looking at erosion that's immediately proximity to the road.
Basically on the road. Yeah, on the road in the ditch. Yeah.
Do you have any sense of the frequency of erosion, substantially downhill that's caused?
Yeah, well, that's a good question because, from my graduate work, there's a lot of erosion below culvert outfalls, and we didn't try to map that or quantify that.
Maybe outside,
Yeah, well, mainly because the different, kind of phenomenon would have required a somewhat different method. And often, if you've got that kind of erosion, then you've got erosion of the ditch line, too. But if you think about eroding gullies below culvert outfalls, that's an extra massive sediment phosphorus that we haven't even accounted for. That's definitely out there.
What about land use adjacent to that?
So we didn't do a land use filter because so much of the Winooski watershed is forested anyway. But then, and there is some analysis. If you look at this chapter of that report, I'm pretty sure that the land use factor came out in that principal components analysis that we did. So we then went back in GIS for the segments that we inventoried and looked were they adjacent to ag or adjacent to forest, basically, because we didn't do anything in any urban areas, any place where there were paved roads, which even in the village centers we didn't do. It was only unpaved. I'm pretty sure that land use did come out, land cover came out to be a factor in the principal components analysis.
Did you have proximity to surface water?
No, we didn't. I could comment on that later, though. That sort of figures into the connectivity story. Okay, what do I do? Okay, so from that survey of road segments, we basically then took for each of those sub-watersheds of Winooski, that estimate of, or the mapped values that we've gotten for erosional features and for volume of those features, and calculated a mean for all of the road segments that we surveyed in each of the sub-watersheds. And you're looking at that mean volume and standard deviation on that for each of those segments. And what you see is that on average, as I said, we've got somewhere about 7 cubic meters of sediment per kilometer of road that appears to be eroding. But there's pretty distinct variability here with these steeper watersheds, the Little River and the Mad River, producing more sediment or with more features evident on the roads. And so if you plot out mean watershed slope against these means here, you see that it's not a super strong relationship, but some evidence that the steeper the watersheds are, this region through here, the higher the level of erosion on the gravel roads are. And here's another way of thinking of that story. I'm skipping over a bunch of what's in the report in the interest of trying to be efficient with the time that we have available here. But what we did with that survey data is scaled it up to the road network, multiplied volumes by a bulk density to get a mass of sediment, and we have phosphorus numbers in the report too. And we came up with this estimate for an estimate of how much sediment is coming off of the road network. Now, if you proportion that sediment contribution out to each of the sub-watersheds in the main stem of the Winooski and plot it up, that's what you're looking at here. And this percentage of the unpaved road network is just what's the distribution of the unpaved road network on a percentage basis in each of those sub-watersheds. And the point of doing this is to show that although 40% of the unpaved road network is located in the headwaters and main stem of the Winooski, those two sub-watersheds only generate a little over 20% of the estimated sediment that we think is coming off of the roads based on our survey. But only about 25% of the unpaved road network is located in the Little River and Mad River sub-watersheds, but those two sub-watersheds look like they contribute over 50% of the sediment that may be coming off the gravel roads. So the idea behind this, or the lesson I think behind this, is that it's not a spatially homogeneous problem. There are some hot spots of activity, and that's probably intuitive for any of you that have driven around on some of these roads. You know, the steep roads and certain kinds of positions seem to be really problematic. I think the important lesson, or thing for us to think about is that if we really do have limited dollars to spend on remediating some of these things, there may be some really good clues to where we want to go and spend our resources, because there may be certain towns, certain places in the watershed that could really use the resources to address this problem. Okay. I'm going to move into the second part of that Lake Champlain Basin Program study, and that was in trying to really quantify how important that sediment production from roads is with respect to what's coming down our rivers. And so this little schematic is just a reminder that if you take sort of a material budgeting framework, these numbers here in this blue arrow are the estimates from Eric Schmelzer's work and Laura Medley's work on sediment and phosphorus fluxes into the Winooski, or down the Winooski River into Lake Champlain. I'll just use this to illustrate that much of what we know about water quality, degradation, contributions of sediment and phosphorus to the lake are drawn largely from studies and modeling work that we've done to look at sourcing from agricultural fields and from urban lands. And then thanks to, I have rivers in here, thanks to the work that Mike has done and Andrew Simon's work that Mike brought to Vermont, we have a better and better sense of what's happening with eroding stream banks and how important they are in contributing to the water quality degradation problem. We have a little bit of information from forested hill slopes. Jamie Shanley and I have done some work up on Mount Mansfield from these headwater streams to try and quantify what the sediment production rates look like there. And so this work was really intended to try to put gravel roads into the picture and ask the question, if you get an estimate of how much sediment is being produced on the roads, how does that compare with what's coming down the rivers? So we situated this part of the project in the Mad River watershed because the Watershed Association there has this monitoring program, as other watershed associations do in Vermont, where they're monitoring water quality. And we knew that we wanted, when we set up the road study, we wanted to be able to not only estimate what was coming off of roads, but what was coming down the streams in the catchments in which the roads were located. So these two plots on the bottom of this slide are just means of samples collected by the Watershed Association for total suspended sediment, which is actually a converted value because they measure turbidity. And so we went out and measured took some samples and used the Rizzo lab turbidity probe to get the turbidity measurement, and then measure TSS on those samples so we can convert their data, and then their data for total phosphorus concentrations in the samples that we've taken. I'm plotting just these catchments because these are the catchments that we set up road segments in to study. And so what we did there was selected 12 road segments in these 5 sub-catchments located in Warren, Waitsfield, and Fayston. And on each of so we selected segments of road that were drained to ditch relief culverts, not to stream crossings. And at the culvert inlet, we installed these double V-notch weirs so that we could get good resolution on low flows, but could also measure the higher flows. Outfitted them with a pressure transducer and ISCO automated water sampler, and then monitored runoff during storms and collected water samples for analysis of total phosphorus. We have a few soluble reactive phosphorus samples and some sediment. And here's what the data from that looked like. This is just one storm in October. This is on a day when I was coming to meet you guys, Jim, and I think you were in that group up in, what's that really steep stream up in Warren, where you guys are doing some post-Irene. Yeah, that's good for us. Yeah. And it was storming like crazy that day. I don't know whether you remember, so we were able to get a really good data set from that day. But this is sort of typical of what this data set looks like, where we have a series of sites. We never had all 12 sites at one time because we were moving equipment back and forth. But for this storm, we have 5 sites that we're monitoring. There are these on this side of the watershed, and a couple of hydrographs and then suspended sediment samples. And this slide illustrates the sort of general pattern that we saw where I plotted out or put on each of these graphs the road length, the segment length that we're monitoring, because in general the runoff tended to follow road length, so you're seeing the greatest quantity of runoff in that longest road segment that we monitored. And as you come to these increasingly shorter road segments, the quantity of runoff declines. But the total suspended sediment plotted as these black dots tends to go more with the road grade. So I haven't put road grade on here, but for example, this road segment is steeper than this road segment, and you're looking at TSS concentrations on a log scale. So you see, you know, we've got higher TSS concentrations, for example, here than we have here, and so on. And the concentrations get lower when you go into some of these lower gradient roads too. So we used data like this from a number of storms at each of the sites in order to basically calculate a load of sediment and phosphorus off of the road segments. And there's a fair amount of analysis between the data and the slide that I'm showing you here. But what you're seeing here is an estimate for each of those sites, not including this Wemple road where the town was concerned about safety of the infrastructure and asked us to pull the equipment. But for the other 11 sites, we have estimates for each storm event that we monitored of a total load of sediment and phosphorus coming off. So we basically scaled that to an annual basis. We have multiple storms that we had scaled out to an annual basis and then took the mean of that. So there are error bars around each of these dots too. And I'm plotting them against road grade primarily to show that as we're looking at a log scale, by the way, on the y-axis, and that's important. If you plot out our estimates of the mean sediment production on these road segments, what you see is that as the road grade increases, we get a pretty substantial increase in sediment production rate per unit length of road scaled over an annual basis. And then the final piece of the analysis for this was to take that statistical model and then basically scale it across the road network in each of those 5 catchments to come up with a prediction of how much sediment was coming off of the road network in each of these 5 catchments, and then to line that up with a best estimate that we could get of what was coming down the stream in those catchments. So Eric Smeltzer actually produced with his model our estimates of phosphorus and suspended sediment coming out of the stream, and then the red bars are my estimates of what are coming off of the roads, and the percentages are the fraction of what's coming down the stream that is represented by the roads. Now, this isn't scaled for the connectivity piece, so I did do a connectivity analysis and did some GIS work to look at how close are culvert outfalls to streams and tried to constrain this number back a little bit. I also want to make the point that there's huge error bars around these estimates. The error bars around Eric's estimates are really large, and the error bars around my estimates are quite large. Nevertheless, it seems sort of intuitively reasonable. For example, in a place like Shepherd Brook, I don't know how many of you might know where Shepherd Brook is. It's in Duxbury as you're going from like Harwood Union High School south. It would be a trip on the, well, here on the left, like 85% or more forested. And so it's got a fairly stable stream channel. An estimate of 20% of what's coming down the stream coming from roads seems conservative to me because there aren't other obvious sediment sources in that watershed. So despite the uncertainty around these estimates, I think they seem like they're in the ballpark for what we might think would be a reasonable contribution for the gravel road network. Okay. So with that work, we were actually doing this other project at the same time, and Donna, Rizzo, and Lesley Morrissey had really gotten the funding for this, and we were asking the question, I forget actually which project we started first, but we're asking the question, what else can we learn from the RGA database? And there were these emergent discussions about what's the importance of roads within the policy context. And so we got a grant to basically take the RGA database and ask, if we can see these kinds of phenomena on the road network, is there any evidence, if you look at the stream channel, that roads may be creating some sort of an effect on the channel morphology? And so this is the second study that was funded by the Northern States Research Consortium that really Lesley Morrissey was the lead on. I use this slide often because I've given this talk in other settings to explain the Rivers program and what you're doing here. I won't explain that to you guys, but we're basically using your data set. And the response variables that we're using are your RGA condition scores. So we're using each of your dimensions of channel adjustment and then your overall condition score. What we did is took your database. Gretchen, I think you helped us with some of this, culling some of this or answering questions that we had. We took your database and looked for reaches where the upstream contributing area was at least 75% forested, because we wanted to get a subset of your database that was reaches that had been assessed where we might be able to assume that roads would be either the only human impact or the predominant human impact. So we culled the data set for reaches that had greater than 75% forest cover, contributing areas that were relatively small. There's no magic around this cutoff. It just turns out to be what the cutoff was to get us these other conditions. Kristen Underwood did a lot of work with us and is a co-author on this paper that we've got in review now to cull out any of the reaches that had impoundments, railroads on the channel margins, any history of dredging and gravel mining, or any development right along, or, well, greater than 10% of the area along the reach corridor that was developed. So we think we have a data set that is primarily natural or pristine landscapes except for road networks. And then we did the entire analysis and started worrying about pseudo-replication because we were doing the analysis on reaches that had been assessed along a profile, and we went back through the data set and just pulled out the downstream-most reach and redid all of the analysis. So what you're going to see is results of the analysis of a series of road metrics against the geomorphic condition scores for the downstream-most reach in the catchment that we selected according to the criteria. That gave us a data set of 102 reaches that we worked with. So if you're asking the question, can you see an imprint of roads on the channel condition for an assessed reach, the question then becomes, okay, how do you, at what scale do you look at where the roads are and what the road impacts look like in the basin? And if you have an assessed reach in a catchment that's been assessed here, it might be that you can see an impact of roads if you just look at the roads that exist in the reach corridor. Or it might be that you need to look at the entire channel corridor all the way up through the watershed and look at how dense or what the road network looks like within the corridor. But it might be a catchment scale phenomenon and not just constrained to the corridor. So you might need to look at the drainage that goes into the assessed reach, or you might need to look at the entire catchment. And so what we did in this part of the project was to use a lot of GIS analysis to calculate a whole bunch of metrics of the road network, and we calculated them at each of these spatial scales or regions of interest. So I'll just quickly show you what these metrics look like. We had a set of density metrics, a set of proximity metrics, and a set of orientation metrics. And the density metrics were intended to just give us a sense of how intensively developed are these areas with respect to roads. So we calculated a binary variable for each of these regions, are roads present or not. We calculated a road density, length of roads per unit area, and then we counted up number of road stream crossings for a density, and each of those metrics was calculated each of these 4 scales. For proximity metrics, what we did is segmented the stream network in 50-meter intervals and then calculated the distance to the nearest road. And then we, for each of the regions of interest, again, we calculated the mean distance, the minimum, the maximum, and the sum of those distances for some indication of how close the roads were to the channels. So in some ways that gets back to your question too. I think it was you, Jim, that asked about distance. And then for orientation, it's a little trickier to visualize, but I'll use some of this graphic to explain this. We segmented the road network into 50-meter segments. For each of those segments, we calculated the orientation of that segment relative to true north. So this segment right here is at 91 degrees relative to true north. This one, for example, is at 25 degrees. It doesn't look like it here. We twisted the image of it, at 25 degrees relative to true north, and so on. And then we did the same for the stream network. So 50-meter segments of the stream network, and also calculated their orientation relative to true north. And then we took the difference between the two for road segments and their closest stream segments. Okay, so you've got two examples here. One where these two roads have an orientation difference of 24 degrees. These two which have an orientation difference of 100 degrees. And then this is meant to just be a little angular diagram to show you that if that orientation difference was between 45 degrees and 135 degrees, we called those roads parallel. So this road would have been classified as parallel to the stream network. And then if that difference was less than 45 or more than 135, we called the roads perpendicular. So this road right here would have been classified as perpendicular to that stream there. Okay, so every road segment and every catchment at each of those four scales got an attribute of whether it was parallel or perpendicular. And then we basically calculated the mean, sum, and percent values for parallel and perpendicular road segments for each of those catchments. So basically what we had is a lot of road metrics, for each of these four scales, sort of an alphabet soup. And we set about just trying to do some sort of intuitive look at whether or not any of those metrics might be related to the condition of the channel. So I'll show you three examples of what that looks like. In each of these, we're plotting the overall geomorphic condition score for the 102 reaches on the x-axis. And on this graph, on the y-axis, we're looking at the number of road stream crossings in the direct drainage. So just one of those four scales. And what you're seeing is that as that number of road stream crossings gets higher, the geomorphic condition of the stream is poorer. And as we have fewer crossings, we tend to have streams in better condition. Doesn't mean it's causal, but it's at least related. Go ahead. So, but your density metrics included, you were looking at density. Okay. What were your density metrics? We had more than what I'm showing here. Could you go back? That's what I thought. But yeah, so I'm only showing you, go back even right there. So we calculated lots of metrics. I'm just going to show you plots for three out of all of these here, but then I'm going to show you a table with a whole bunch of them with some summaries. Yeah. So here's a second example, same construct on the x-axis, but now we're looking at one of those proximity measures. This is the sum of the distances from streams to the nearest road. And here what you're seeing is as that distance increases, as the roads are farther and farther away from the channels, we tend to see channels that are in better condition. And as that distance gets smaller and smaller and the streams are closer to the channels, we tend to be looking at channels that have been scored as in poor geomorphic conditions. And those distances are in meters on the 50 to 100? They're in meters. Yeah. So if the mean of a set of segments that was scored as poor would have had a mean distance of somewhere on the order of, what, 60 or so meters. Of all the channels, of all the reaches that we assessed in our data set of 102, of all of those that scored out as poor, according to you guys' assessments, the mean of the distance of roads to the nearest stream was 50 meters. Does that make sense? Okay, and third example of that, this is percent of the corridor roads that are parallel to the stream. A little bit harder to imagine this, but if you imagine that stream corridor and that each road that ends up in a corridor for any of those 102 assessed reaches gets attributed as parallel or perpendicular, and then we say, okay, for those roads that fall in the corridor, what percentage of them are parallel or perpendicular? Here you're just looking at the percentage parallel, okay? And so as we have a higher percentage of roads that are parallel to the channel in the corridor, what we see is that the channel condition tends to be poor. And as that percentage declines, the channel condition appears to be better. Does that make sense? Okay.
Can I ask one more?
Yeah.
Sorry. Did you look at just density of roads?
As opposed to,
As a point you look at, in this case you looked at its orientation, its proximity, but in terms of density.
so here's the, I'm going to try and walk you through this table a little bit to get an overview, but here's a recap of those metrics that I mentioned on that slide of what we calculated. Thank you for helping me. So one measure of density is just a binary. Are they present or not? Another was a typical road density measure, length per area, but another was a density of actually stream crossing culverts, number per area of the watershed. So there were multiple density measures, multiple proximity metrics, and multiple orientation metrics, but then we calculated them at each of these scales. Maybe I'm still not.
Well, the only reason why I'm asking, we have road density numbers per watershed, and determining, it's pretty darn significant. Yeah. When you look at a watershed or county or even town level.
Yeah. Significant as a predictor of what?
And determine that is a potential predictor of impact, water quality impact.
Okay.
So that's why I'm just trying to tie into a density value to impact.
Okay. Yeah.
Did you look at both public and private roads?
We used the E911 data set, so I think that's pretty complete, but some of you from VTrans could weigh in there. I think E911 even includes driveways. That's all right, John?
I'm not certain, but I would think so. Private roads anyway, I don't know about driveways.
But they don't include farm roads, the private road,
Logging roads,
private roads.
Exactly.
Does that include class 4 town roads in your data set?
Yeah, because that's in the E911 database.
These are just perennial streams?
Yeah, we used the Vermont hydrography layer, which is pretty fine scale, but wouldn't include like intermittent streams. Okay, this is the last slide in this part of the presentation. It takes a little bit to sort of take it in, but the questions are kind of helpful because they help you get a sense of the range of metrics that we're looking at and the scales at which we were assessing. Is there a relationship between the metrics and the geomorphic condition of the stream? Okay, and so when you see a statistically significant finding in a box, that means that metric at that scale was a significant predictor of channel condition. So if you step back from this, this has been we're revising the paper right now, and it's been sort of challenging to think about, well, how do we interpret this? One interpretation might be, these are just two different ways of thinking about road stream crossings, but one interpretation might be that road stream crossings are a pretty good predictor of channel conditions. The more road stream crossings you have, the more degraded, as you saw in that first slide that I showed you, channels tend to be, and that does a pretty good job of predicting across every scale that we've looked at. On the other hand, there are some metrics like this binary metric, whether roads are present or not, that might be a predictor if you only look in the corridor of the assessed reach, but that's the only scale at which that metric is a good predictor. Okay? So this exercise is a bit of a statistical sort of probing. What could we learn from the geomorphic assessment database with respect to road impacts? The interpretations of this, are a little bit trickier because then you end up with all these metrics with statistically significant results. So that's how I am thinking of it, is can we look at this and figure out whether there are strong predictors across all scales or certain predictors that are kind of constrained in the scale at which they help us understand impacts of the channel, if it is causative at all.
Was the sample well distributed across the channel conditions?
Yeah, there were not many pore reaches. So there's a point, and I think the latest version, Donna, Rizzo, and Allison Vichenik have done all of the statistical analysis. And I think in this latest version, they've decided to lump the pore and the fair together into one class. Yeah, good question. That was a challenge. I feel like we talked to you about that. That region was a big help during this. Others?
Yeah, I was just thinking one other metric that would be interesting to look at would be the total area of roads, not just the density of roads, but width and length, and whether that adds up to a significant percentage of impervious.
Yeah, although in these landscapes, in these watersheds, there were probably some of the road corridor, or the river corridor roads might have been wider paved roads, but a lot of them are gravel roads, and then most of those are all the same width. So I suspect that the area would correlate really strongly. Look at the length.
So we have that information. We have percentage of impervious that are in roads and roads. Yeah. Per town. Yeah.
Okay. Oh, there's part did you refer?
Right. Yeah, it's pretty much the same question.
Okay. Okay. Last piece that I'll describe is this most recent work that we've been doing in collaboration with Better Backroads program. John and Alan May not here today, and with support from Carrie's program, which was an outgrowth of the Lake Champlain study. I think Carrie came to us and said, "I really want to know how effective BMPs are." So we started the study 2 years ago to look at the effectiveness of BMPs. And there are two pieces to what we've done here too. Let me see. I should say this is here just to say that we're working using the Better Backroads, working in collaboration with the Better Backroads program and using their archive. There are two pieces of what we're doing here. One is an experimental evaluation of BMP effectiveness where we're actually treating road segments with BMPs, and I'll describe that and looking at the results. And another part of it was a retrospective analysis of past projects. So we went back to the archive of past Better Backroads projects and looked at how they fared over time. And I'll briefly explain each of these. So the experimental part of the project involved selecting a set of road segments. We piggybacked on some of those that we had studied for the Basin Program project, but chose more in collaboration with the towns. We were back in the Mad River Valley for this. We met with the town select boards. We went out in the field with the road crews. We used that assessment that Andre Rizzo and the Friends of the Mad River had done in that watershed to look at places where there was road impact. Dan Courier at the Central Vermont Regional Planning Commission helped with that assessment. So we sort of built on that database of where were there problems with roads that the towns might want to treat anyway. And so then we selected a set of road segments that the road crew or the road foreman had said, yeah, we would like to do something here, and paired each of those segments with a road segment that we would hold as a control and not treat. And then we installed silt fences at the outlets of culverts for each of those selected road segments, paired a controlled site with a treated site, and for a series of storms, measured the mass of sediment coming off of the road segment. So after each storm, we would go out, shovel the sediment out of the silt fence, count the number of 5-gallon buckets that we were shoveling out, bring one bucket back, dry it to get a dry fraction of that, and then subsample for it, which analyze those subsamples for total phosphorus. So you're going to see a lot of plots, or 2 slides of plots like this, where each dot represents a storm event. And what I'm doing here is trying to establish a relationship between a controlled and a treated site before the treatment has gone in. So even though this site is a treatment, these data points are for those 2 sites for a storm, represented by a point before the site was treated. The intent is, we're still in the middle of this project, is to test 4 treatments: a stone line ditch treatment, compost socks, check dams and turnouts, and it's looking like we probably won't get this grass seeding treatment because we were planning to do them in Warren, and they had so much storm damage last summer they couldn't follow through with the project. So I'll show you now just the stone line ditch treatment and the compost sock treatment. These are 3 sites. Randall and Cubasser roads are in Basin. Ski Valley is a waste field. These were treated at the end of 2012. This one we just treated this last field season, so we don't have many post-treatment points. But what you see in each of these plots is this controlled versus treated site, what the relationship looked like for the storm events that we monitored before the BMPs were put in, and then what happens after the BMPs go in. And we just don't have very many points yet for the Ski Valley Road. But in each of these cases, if you look at the magnitude of sediment produced, so each of the points is a sediment dry mass, too. If you look at the magnitude of sediment that's being produced during a storm event, it's pretty high on these segments that were selected for treatment. Remember, the road foreman was saying, yeah, we need to do something about this road segment. And then once we treat it, those levels of sediment production for a storm event come way, way down. So it's only 3 sites for the 3 replicates of this treatment, but across the board, this treatment looks to be quite effective in reducing sediment production at the site. Here are the results that we have so far for the compost sites. The Bragg Hill site is in Fayston, and in the pre-treatment period, you're looking at storm events that were mostly small, 1 larger storm event in the sediment production across the 2 sites, and then not as clean and clear of a picture, but a clear reduction in sediment production in the post-treatment period. That story is a little bit more muddled for the 3-way site. This is in Warren at the intersection of Sonore, Prickly Mountain, and Fuller Hill Road. That's why we call it 3-way. And in the post-treatment period, we had a lot of problems with the monitoring. So we only have 3 points that we can plot up now. The road crew, Warren got a lot. Are any of you from Warren, live in Warren? They got a lot of storm damage last summer, and so they had to completely reshape the ditch before the compost stock went in. This is from this upper Prickly Mountain site, and we're not seeing any change. In fact, it looks like a little elevated sediment after the treatment, but it's almost surely because of the ditch work that they had to do before the compost stock was going in. The other thing I'll just draw your attention to is the magnitude of sediment production on the y-axis. The magnitude here, did you go back one slide? Is sort of on the order of the magnitudes that we're seeing at these sites. And I think the lesson in that, if you go forward now, that Alan May would agree with is these were not ideal sites for compost stock installation, and we didn't realize that before the storm damage of last summer because they had reasonably well vegetated ditches. They looked like places where we might install a compost stock and see this kind of result. After those summer storms last summer, they became really erosive, highly erosive. So I think the lesson in this, the lack of a effective result here, is that there's going to be some site limits to where you'd want to install this kind of a treatment. We just got the stone check dams and turnouts installed in Duxbury right before the snow fell last November, so we'll hope to have results from that this summer. And it looks like we're not going to be able to test the grass seeding treatment unless we can get a town to volunteer to come forward to do that. But at least we'll have these 3 treatments to look at.
You played around at all trying to normalize those for flow?
No, but that's a good question. We don't really have a flow measurement. We have rainfall measurements because for every storm, and I'm trying to figure out now, I was having a conversation with a grad student about it yesterday, could we compare these estimates? I feel like they're pretty robust relative to our ISCO measurements of mass coming off of roads and sort of spread it out over a year and compare that to what we estimated from the ISCO measurements. I think that our estimates for Lake Champlain report were probably pretty conservative considering what we're seeing here.
Conservatively low?
Conservatively low. Okay, just one more piece on this. For each of the samples that we shoveled out of the silt fence, we did a grain size analysis just to look at what fraction of that sediment was fine, thinking that for the reason that it should be the fine fraction that the phosphorus is attached to. I had thought that they would come out quite coarse, and we would have to scale back those numbers by a lot before we multiplied them by a phosphorus concentration. But for the most part, the fine fraction is pretty high, over 60% at each of these sites that I'm showing you here. and pretty close to 100%. At Bragg Hill, that site that has the compost stock on it. So what that basically means is when I was drawing your attention to the y-axis and the magnitude of those masses, for any of those, we wouldn't multiply that mass by the sediment concentration, by the phosphorus concentration per se. We would scale it back first and say what's the fine fraction coming out, and then multiply that by a phosphorus concentration. So I haven't worked all the way through these results to give you an estimate of how much phosphorus now it's coming off, but we have the data to do that, and that'll be the next step. Okay, the second part, this really is getting close to the end. I'll just tell you this last little part and then wrap it up. The second part of this ERP-supported study is to do this retrospective assessment from the archive of past Better Backroads project. And this is just a schematic to show you that although the Better Backroads program has funded a whole range of kinds of BMP installations, for the purpose of summarizing them here, I'm going to break them into these 4 different types. So we went out and looked at a whole range of past projects that fall into essentially stonework type projects, revetments that are meant to stabilize an unstable stream bank where there's a road above and typically either a stream or a lake or pond below, different kinds of soil stabilization treatments, and then culvert replacement. One thing that we wanted to be sure of when we did this is that when we went out and looked at projects to assess that they were somehow representative of the program's past projects. So the program has been around since 1997, but the paper records of projects really only exist back to 2004. They've been lost before that time. So we went back into that archive and just selected 3 different years, looked through every project that was funded for each of those 3 years, and just looked at what class they fell into. What types of projects did the program fund over time? A little over half of what they funded are stonework projects. Roughly around a quarter of what they funded are culvert replacement or culvert installation projects, and the rest there. And this pie graph at the bottom here is the distribution of the kinds of sites that we looked at, the kinds of BMPs that we looked at. So pretty close to that distribution. We ended up at a number of sites up in the islands looking at revetments, which is the reason why we have a few more, or a few fewer here, and a few more in some of these other classes. We visited 46 sites located in these towns that you're seeing on the map here. Each of these, almost all of these sites, projects, involved more than one BMP installation, so there might have been a stone line ditch and a culvert replacement or some grass feeding and something else. So all in all, there were 106 BMPs, individual BMPs that we looked at. For each of those BMPs, we developed this 3-tier scoring system where we, Alan May helped us sort of look for what to look for that we should use to assess whether they were performing. And then we class each one as either intact, compromised, or failed. So here you have a culvert that's been installed as part of a project. It's still passing water, but there's debris at the inlet. So this would be a case where we would have called this BMP compromised. Eventually, it probably won't function as intended. Here you've got a place where there's stone lining put in a ditch with a vegetative fabric below it, and the whole thing has blown out. So we would have called that failed. I'm just going to show you 3 slides of different variables that we looked at in order to sort of probe what the outcome of a BMP was relative to possible explanatory factors. So the first thing we asked was, how long do these things persist over time? Are they all intact if we look at a historical archive, or do they all blow out? And so what we've done to address this question is we're plotting here a set of BMPs that we looked at 11 sites that were just 1 to 2 years post-installation. And then here between 3 and 5 years post-installation, and here between 6 and 8 years post-installation. And then what you're looking at on these graphs are these different kinds of treatments. Okay? So, Justin, could you go up again one more time just to get rid of these 2? So if you looked at the sites that have just been installed very recently, for the most part, they're still intact. There are a few that are compromised, and there was one vegetative control that had not, had failed, if you you look at sites that were pretty close after installation. If you go out to sites that have been installed in that 3 to 5 year window, we start to see more of them are compromised. Typically, the stonework projects more often compromised, but still pretty large rate of success, if you call success, that the BMPs that have been installed and paid for are still on the ground and functioning as intended, and really only a very small number, 5 of them, in that window of time out of 54 that we assessed that had failed.
So, are you assuming no maintenance?
Well, that's a good question. We don't have any real information about that. That's a really good question. We've asked those kinds of questions to the road foreman, but we don't have a really good database for it. So, no, we don't know. If you go to the sites that are the oldest that we assessed out there, you begin to see this sort of lifetime issue appearing that, oops, sorry, they do have a lifetime, and that, as we move our way out, we've got only 17 BMPs at 12 sites in this data set, but you've got a more even spread that you're beginning to see if they have a lifetime, and they will probably degrade over time. Yep.
So did you happen to find or observe that there's like a certain set of stone projects that always fail, or some projects fail more than others?
Well, we're sort of trying to work through that now. Joanne Garten, the grad student, is working on this with the statistician at UVM today, because we're trying to take some of these variables that we've got and then look at, can we predict whether they fail depending upon road age or the placement of the road on the hill slope and that kind of thing. I can't answer that yet. I'm hoping that there are other factors that we measured that would help explain where they failed. Got a bit of a hint in that in the next 2 slides. So we're also interested in knowing how they performed relative to road grade. So these are similar kinds of plots where we're just plotting out those sites and BMPs that we looked at in 3 different classes of road grades: low gradient roads, sort of mid gradient, and very steep roads. And what you see is that virtually across the board on all those low gradient roads that we looked at, the BMPs were entirely successful. None had failed. When you get into these mid gradient roads, we have more of them that were compromised, and still only 4 out of 29 that we looked at that had failed. But when you get into this highest gradient road, then you start to pick up more of them that have failed. So pretty intuitive, and I think what you're getting at, Gary, that there are certain conditions that suggest that the BMPs might be more challenged and they're persistent. And I don't think this is our final say on this, but we are also wondering to what extent the exposure of any of these road segments that have had treatments on them have been exposed to big floods, whether that has something to do with their failure. We know that our landscape has been really hammered in the last few years. So what we did here, I'd be curious if anyone has better suggestions, is you guys know this, that GIS layer that has been created of the flood impact zones in Vermont, where it started out as just people drawing circles on the map, and then someone put it into GIS, and if it's in GIS, they will come. So we basically overlaid that GIS layer with our points and then just attributed, had any of these road segments been exposed to any of these extreme floods, basically since 2004, since the date of the project, because these are projects that have been constructed all the way through time. Now, just like your maintenance question, what we don't know is if a road was exposed to the flood, did someone go and fix it later? So we don't know. When we then went and looked at the project, if we said it was intact, we don't know if it was intact. If it was also exposed to a flood, we don't know if it was intact because it made it through the flood or because someone went back and fixed it later. Yes?
Beverley, the previous slide with the slopes.
Yeah.
How many years after installation?
Pretty much the same. So average age 3 to 4 years. Sorry. Average age 4 years and average age 4.9 years. So because I'm only graphing one variable at a time, but every single one of these has an age, so that's what we're trying to tease out now with the statistical analysis. If we put in the resulting condition and each of the variables that we've measured, flood exposure, age, gradient, road position, road profile, whether roads are ground or not, do any of those help predict the outcome?
These were all Mad River Valley again?
No. These were, could you go a few more? Going here. So some up in the islands, most in central Vermont. We didn't get down to southern Vermont at all.
So really, was BMP tending to be at the top of a road segment in the ditch or somewhere in the middle of the ditch? I mean, I've worked in some towns where town line is in the middle and one.
Well, that's a good question because they're all Better Backroads projects. So they're all the way a Better Backroads project works. Typically, the way this will work is there's a problem road in a town, and the town gets wind of the fact that they can get funding through Better Backroads. So they apply for it, and they do the work in an area where they can afford to treat and can get the money from Better Backroads.
So the segment where somebody treated it may have a ditch upstream of it that's still not in good condition.
Absolutely. And if it were over a town line, then it would really be an issue.
Right, or how successful the BMP is if it's really
Absolutely. Definitely. You're here?
One thing that would be interesting to see compared with is like if there was a way, sort of the way you were doing your earlier presentation, where you could see, okay, what's the frequency of failure of something that hasn't been treated with a BMP, that you could see, like, okay, how frequently does that road fail, that treatment or whatever way of dealing with it fail compared to, what's the lifespan of that compared to BMP.
Yeah.
And I think that is another kind of
We did think about doing that kind of thing because we thought about trying to take the Better Backroads archive and then pair it with another site, but we felt like retrospectively we couldn't be certain about any sort of pairing, and that there are so many different variables out there, that I've mentioned already, that to be confident that you truly had a pair would be sketchy.
Is that what you're taking what Kelly said? Is that what you could do now moving forward with your pairs?
Yeah. Yeah.
How successful does it survive?
Yes, except that, and John has made this point, in those treated controlled sites, they're not perfect pairs in every way. Sure. They are monitored in a pre- and post-treatment period, but if you look at the magnitude of sediment produced off of them, in almost every case, those treated segments were big sediment producers, and that's why the road women wanted to treat them. Did you have a question?
Could you go back one slide? So do we typically recommend stone grass mining when we're above 5%, or does Backroads recommend?
I don't think so. But what might have happened in a site where you're seeing grass in one of these high gradients is a project where there was stone line in and they went and hydroseeded behind it, which is exactly what Warren did in those two projects that we did there. And so we would have looked at both when we went. So I can't tell you without going back and looking at the database whether something you see here in this graph or this graph is vegetative treatment with alone or in combination with something else. But you can tell from the number of BMPs and sites that virtually every site had more than one kind of BMP on it. Does that answer your question?
Well, it does, but I just was wondering, it looks like if you look at the, the frequency of failure, that it's a lot more variable with stone than it is with grass.
Yeah.
And if grass did hold up all the way through, it seems like it's a more predictable BMP.
But it doesn't buy you much, I doubt, in terms of sediment reduction. Like if you're going to grass seed a road that's a 14% grade, it would be really challenging to get that grass to grow.
In all respects, but have you not used it above 5%? Okay.
One of the questions I had was kind of going to the geology side of this. Have you ever looked at try to put in where our glacial lacustrine line is on these watersheds versus till?
Yeah.
I know many of these roads, there's a definite break point that you hit where you leave the lacustrine and get into the till.
Yeah. I think we're going to end up doing that for this data set. I had just gotten a hold of Kristen about 2 weeks ago to talk to her about it. I don't know whether you know, she's had some pretty severe back problems.
Oh, I didn't know that.
So we're waiting for her to get better.
Yeah.
But yeah, I do think that sort of underlying glacial history probably is another factor that explains whether these things hold up or not, and also some of the hydrology.
On the phosphorus, I would imagine as well.
Yeah.
When you talk about culverts, are you talking about stream crossing culverts or culverts in the ditch itself, and knowing that if it's more of the former, we recently are changing our standards to reflect a larger geomorphic condition, hydraulically and geomorphically. And if it's the latter, we're also, as we said, changing the road and bridge standards, increase the culverts for the actual ditch network. So when you talk about culverts,
it's too bad that Alan's not here. You know, again, we're just mining the archives of the Backroad project, so it's whatever was in the project files. My sense, although I could go back and look for you, my sense is that most of them are culvert replacements and not ditch relief culverts, because when you look at some of those files of the project, when a town goes and applies for Better Backroads money, instead of just using their own town budget, they're usually pretty good projects. So they're something that costs as much as that.
I know in the past 5 or 6 years, up until last year, we tried to shy away from ranking grants high that were on streams. I mean, that were actually stream culvert replacements, because those have some other funding sources available. Partly, and they tend to cost somewhat. You know, these are only $3,000 grants. So.
I could go back and look though. This is my wrap-up slide, just some concluding remarks. I think in thinking about these various pieces of work collectively, a few lessons that sort of maybe are takeaway, or a few takeaway points are that this idea of trying to put the road story within this broader context by using this material budget or sediment budget framework is a useful way of thinking about how important these things are. You know, is it a small percentage or is it a big number with respect to what's coming down the streams and rivers? And I will be the first to say there's still a lot of uncertainty there, but we've tried to make an attempt to get a handle on that. I think we can come away from this work with some level of confidence in saying that, roads, these back roads are something that we need to pay some attention to, that they do have measurable impacts on water quality and channel morphology. Probably not, certainly not the biggest player in the basin, but something that we could probably improve upon. And that these BMPs do offer the potential to reduce water quality degradation, that they buy us some water quality improvements and persist for years, not forever, but for multiple years of time. The latest thing that we're trying to do before we finish up this ERP grant is do a sort of a costing out analysis of what these things cost for a couple of typical towns, what the scope of need would be if they were to treat, say, the steep roads, and then we've gone into their town budgets and talked to their road foremen about how do they spend their town budget. And so we're trying to do a kind of a cost analysis of what are you spending every year to fix the problem, and what would it cost if you spent $15,000 to stone on that ditch, and get that to that point. But that's sort of a good segue into this last point, and that is that the nature of this problem is not just a scientific one, but really a sort of policy and management one. And the multiple stakeholders involved and the multiple levels of governance that we have around transportation networks that range from the town to the feds, really leads up to the state level, and the governance structures that we have around water quality and how do we make those two things come together are really the challenges that we need to face next. And that's going to take people with expertise other than the kind that I have. But I think having the scientific information to sort of support those challenges is useful. And then I just want to finish by acknowledging the people that have worked on this, particularly the students that have been out in the field and done a lot of the really hard physical labor, and also the funding sources that have supported the 3 studies that I've described today. And I'm happy to stay around for questions, but I know you guys have been sitting for a long time too, so I won't be offended if you want to take off.
Just one more.
Yeah.
Back on that previous slide,
Yeah.
your closing statement, you mentioned BMPs have the potential rather than are effective at?
Yeah, that's why I hesitated, because, could you go back one slide? Because I was a little concerned that I hadn't put the word in degradation. But yeah, I mean, they are effective. They have potential to bias improvements in water quality. If we're going to, if the question is, are we going to get anything for the investment, I think the answer is for certain kinds of practices, yeah.
Well, were you planning on doing any like further analysis on some of the effectiveness?
Yeah, the last part, this project that Carrie's program is funding, we are not done with. We've got another whole field season, and we've got, a fair amount of economic analysis to do. Yeah.
I was curious on your Shepherd Road example, you could almost account for 20% of the sediment.
Shepherd Brook.
Shepherd
Yep.
Brook from the road.
Yeah.
And so has there been any effort to look at the trail, tote roads? Did anybody ever looked at those class roads, the old logging roads?
No. I'm hesitating because I'm not sure that there are many in Shepherd Brook. Do you know Shepherd Brook?
No, I don't. I'm just saying, you said you couldn't figure out what the other sources of sediment were. I mean, if you attributed it to 20% of the roads, and I'm going to your USGS study with Jamie Shanley, maybe there's some natural background.
Well, there probably is some natural background erosion. There's probably a little bit of erosion from the channel banks, although that channel is pretty stable looking, small stream. It's a high gradient stream. A big part of it might just be the uncertainty. There are big uncertainty error bars on each of those two bars. So even though I've got a number and I'm saying that number is 20% of Eric Smelter's number for what's coming down the channel, there's a giant error bar on Eric's number and there's a giant error bar on my number.
I'm just trying to kind of think of what other possible sources there could be. And you do see occasionally, I mean, there are a lot of old logging roads. A lot of them are.
I don't think there are in Shepherd Brook, though.
Okay, I don't know about Shepherd Brook. I'm just saying in general that, that there are potentially, these ancient roads that, for lack of a better term, I guess, trails that they aren't mapped, but obviously some of them, I mean, I've seen some that are clearly leaching sediment, but what
That's the conversations that I first met Gary over. So what about the forest roads down there?
Right. It's probably pretty easy to pick out a LiDAR, too.
Yeah.
Show up pretty readily.
Because of the vegetation?
Well, they just show up as the landform.
I mean, the first that I started looking at that was with Jim Ryan down in the White River area, because they had done one of those first road assessments that the Regional Planning Commission had worked on, and there were places where the roads were completely. Yeah.
Did you have any comments on the Better Backroads manual?
No.
Okay.
I have some comments about the whole, execution of the program, given what I've learned in working with the towns. And, Alan and I have talked about this a lot, and we just started talking more with John as Alan's moved into V-Trans. It's, it's a challenge for a small town to work through. The towns that have gotten Better Backroads grants, I think, feel confident that they can do it now. But we worked with the towns last year where they had a new road foreman, and it was really intimidating for him to fill out the spreadsheet to come up with the cost estimate. And so that hurdle, is not a trivial hurdle for a town if they don't have a particularly, savvy town manager or administrator, and the road crew is used to just doing the field work and doesn't know how to sort of finesse the funding angles. It's hard. There are, 274 of those out there. So it's a big realm. I think maybe working towards some workshops with towns where you sort of help people work through examples. We're setting those up for you.
Yeah.
The next RFP.
Cool.
Yeah.
So the Better Backroads
do a webinar.
manual, for all intents and
ACDs that
purposes,
do our
we're advocating the use and deployment of practices that are probably the best that we can come up with at this point.
Yeah. I mean, I wouldn't say that I'm really expert in being the person to critique that manual, but it looks to me like the kinds of practices that are recommended, if we test them then in the field, they appear to be, so far, relatively effective if they're put in the right kind of place. Like the the lack of an effective result on that one road in Warren is probably because you wouldn't normally suggest that kind of the MP on that kind of a road. Yeah.
There's a few things in there, like there's some retaining wall structures and some bioretention type structures that no one's ever applied for.
Really?
That I think that doesn't mean we should take them out, though. I don't think, but people, the towns don't seem that interested.
Are these all available on the Mason Program website, or something?
No, the Lake Champlain study, so that runoff and the stuff that Jim Peace was just asking about, that's all in a report that's on the Basin Program website. This project that we did looking at the RGA, the River Management Program data set, we have a paper that we're revising now and just about ready to send back to the journal. So if you want to see it, once we're ready to send it back to the journal, we could send you guys copies. And then the third part we're still in the middle of, so we don't have anything written up. I mean, we're actually going to have to give Michaela some kind of a final report for your share of the money, but it's going to be preliminary because it's only going to have those 2 treatments in it. And we haven't done the rest of it. It's a co-funded ERP and water center project, and the water center money goes for another year.
I think it's maybe an interesting twist in your last part. When I'm working in town, so I'm doing like an intensive amount of Better Back Road projects.
Yeah.
In some parts of the town and other parts have yet to be done. Those areas that we did a lot of work on troubled roads withstood the Irenes and the flash floods.
Yeah.
And the town and ones that haven't been done yet have fallen apart.
Yeah.
I think that's an interesting.
Yeah. After the July damage, John, can you remind me? You might not know who I'm talking about, but there's someone who works for VTrans, Michael will know, who lives in Huntington, Jim Segali, who asked us if we would go to Huntington.
Right.
And so we've done this sort of little case study on Huntington, where Arrowwood Environmental had mapped out where the flood damage was, and we're trying to look and see if is there anything about those sites that we can, that looks like it might be what's creating the locus of the damage, although it probably has a lot to do with the intensity of the storm. But as part of that effort, Joanne, the graduate student, spent a whole day with the road foreman driving around and more or less said what you said. In places where they put stuff in, it's really stood up, and in places that have really gotten hammered or where they know they need to do something and they haven't had the resources.
I wonder if the quality of the installation or the designs has improved at all over the past 10 years or so.
I wonder. I wouldn't be surprised if it has. Like one window into that is in the select board meeting that we were at in Huntington with Yogi Alger at the table. He said, I'm putting much bigger rock in now because the kind of storms we've had, and we've seen some stone-lined ditches wash out, it may be because the rock's not big enough. So that's one example of it. They may be getting better at it.
Also, I think whether it's town or contractors, I think having someone do a pre-construction meeting and
Makes a big difference.
putting in stone-lined ditches, you don't just say, okay, we're going to put in 500 feet of stone-lined ditch and let the contractors, but someone needs to map out exactly where to start here and here, where in relation to the road shoulder, is it going to be right next to the road or something further away, how the depth. It seems that there may be trivial little issues, stone size and all these little things that I think may trigger why some failed.
I mean, Alan made that comment about that last set of treatments that went in November. He wouldn't have put them in like that. So there's a point to that.
Yeah, and there's been some discussion about whether it was placed on fabric or not.
Yeah.
Whether or not, there's a big decision point, sort of, whether or not we should continue to recommend that.
It's checked in, so whether or not to put them in.
Yeah.
Whether putting across culverts or turnouts. Different people might look at a site and make different recommendations. May or may not be the right one, or you could do it both ways and get the same results.
Yeah. Should I answer any questions from people on the webinar?
There aren't any.
Sign off.
Oh, there might be one. Can you read that from Blaine?
Hi, Blaine. Go on.
Different.
He's here.
Is he in the room?
No. He's probably out of bed.
If I understand the question. So, Blaine, if I understand the question, I think it might be the same question that Mike Klein was asking about if you look at, like, the glacial geology map, for example, if you overlaid any of these sites with either topographic metrics, or Mike was suggesting, you know, glacial lacustrine deposits versus alluvial sediments or that sort of thing, the more uncohesive stuff up on the hill slopes, might that be a factor? And my answer to him was, yeah, it's a good idea, and I've been thinking about it. We haven't gotten to it yet. Not positive that's your question, but thinking that's what you're asking. Other physiographic features.
Aspect.
Yeah.
Maybe.
Thank you.
Great. Thanks.
Yeah, thanks for hanging out this long.